Alright, these are your notes for section 7.1, and it's on interpreting polynomial graphs. The first thing we're going to do is review real quick what a polynomial is. A polynomial, the definition is a monomial or the sum of monomials. Alright, and here's three examples. You've got 6, 6x cubed, and then x squared plus 5x minus 4. Now all of them are polynomials. Each one's a special type. This first one is called a constant monomial. It's a constant monomial because it's never going to change. It has no variable on it. It's going to stay 6 no matter what x value we have. The second one is just a regular monomial, because it has one term, 6x cubed, it's all there together, it's just a monomial. And the last one is a polynomial, and more specifically, it's a trinomial because it has 3 terms to it. Alright, but what I want you to know is just that all of them are considered polynomials. Now the next thing we're going to talk about is degree and leading coefficient. Now the degree, we've talked about this before, but it's been a while, the degree is the greatest exponent. In the polynomial. So if you have one term, it's just going to be the exponent on that term. And I should specify it's the greatest exponent on the variable. It's never on a number. It's never on a coefficient. But it's on a variable. Okay? If you have several terms, like a trinomial, then you want to pick the term that has the biggest exponent, and that's going to tell you what the degree is. The leading coefficient is the coefficient of the term with the degree. So it's just the number out in front of where we get the degree from. We get 3 examples here, and for each one I want you to give the degree and the leading coefficient. First one, 7z cubed minus 4z squared plus z. Each one of them has a z. There's 3 terms there. The biggest exponent is a 3, so our degree is 3. And then the leading coefficient is the coefficient on the one where we get the 3 from, so it is 7. And that's all we need to do. The next one, 8 plus 6a cubed minus 4a squared. Well, the biggest exponent is a 3, so the degree is 3. And then the leading coefficient comes from the term where we got the degree from. The leading coefficient on there is 6, because 6 is on the term where we got the 3. Last one. 9y minus 3y squared minus y to the 4th. Biggest exponent is a 4 in this case, so our degree is 4. And then leading coefficient, there's no number written out in front of that term. There's a negative sign though, which means that the leading coefficient is -1, because there's nothing written, it's understood to be a 1, and then it's negative. And that's how you find the degree and the leading coefficient. The next thing we're going to look at is going to deal with the degree a little bit, and it's going to be graphs of polynomial functions. We're going to look at 3 things. We're going to look at real zeros and roots, the degree, and then end behavior. Now we should know what real zeros are. Real zeros are roots. That's how many times a graph crosses the x-axis. And where. The solutions, remember, are where it crosses the x-axis. So if we're looking at our picture over here, it crosses here, here, and here. So it would have 3 real zeros. Okay? Nothing too difficult. You just want to look and see how many times it crosses the x-axis, and eventually where it crosses the x-axis. Now the degree is how many times a graph switches or changes direction. Alright, so if we're looking at this graph, well, it starts by going down, and then it shifts by going up, and then it goes down again. So it changed direction 3 times. So our degree here would be 3, because it changed 3 times. That's what we mean by switching or changing direction. Now that degree is the same as the greatest exponent. So on those examples we did earlier where we picked out the degree, these things here, that tells us how many times our graph is going to change direction. So for each one of those, the first two change 3 times, like our example here. The last one changes 4. It changes direction 4 times. That's a connection that you're going to need to know, how many times it switches direction and the greatest exponent. So make sure you understand that those, it's the same word, and it means it's got 2 different meanings depending on what you're talking about, whether it's given as an equation or an expression, or if it's given as a graph. I've got 3 examples here, and for each one I want you to give me the number of real zeros and the degree for each graph. So 2 things, D and RZ. Okay, graph 1. Real zeros, remember, is how many times it crosses the x-axis, and this one crosses 5 times. And then the degree is how many times it changes direction. Well, we go up and then down, there's 2. Go up again is 3, down again is 4, up again is 1 more, so the degree is 5. In this case, the real zeros and the degree are the same. Now, your degree should never be more than your real zeros. Okay, that's something to remember. Degree cannot be more than your real zeros. Second one, real zeros, degree. Real zeros, again, is how many times it crosses the x-axis. This is actually the line we're looking at. It doesn't cross the x-axis, and it's parallel to it. It's never going to cross, so our real zeros are 0. There are none. The degree, well, it doesn't change direction at all, so the degree is 0. Okay, both of those would be 0 in this case if it's a horizontal line. The last one, real zeros degree, this one crosses twice, so we have 2 real zeros, and then it goes down, up, down again, and then up 1 more time. So our degree is actually 4. And in this case, our real zeros are less than our degree, which is okay, but remember your real zeros cannot be more. Next thing we're going to talk about is how the leading coefficient affects what the graph looks like. Okay, the leading coefficient here tells you which way the right side of the graph is going to point, and this comes in handy when we talk about end behavior. Okay, so if our leading coefficient is positive, then the right side of our graph is going to go up. And if our leading coefficient is negative, the right side is going to go down. And we'll look at some examples here in a minute. Now we're going to tie degree into that. The degree in the graphs we look at. Odd versus even. Okay, so we picked out what the degree is, how many times it changes direction, but we're going to be more specific where it's odd and even. If our degree is odd, that means the ends point opposite directions. One's going to point up and one's going to point down. Okay, one up, one down. If it's even, the ends point the same direction. Okay, and by ends we mean the end of the graph. So both of them will point up or both of them will point down. We've got 4 things we're going to fill in here, and I'm just going to give you basic examples. It could change depending on what your degree actually is, but we're just going to classify it as even or odd. First one here. Our leading coefficient is positive, which means the right side is going to go up. And then odd means one of them's going up and one of them's going down. Well, if our right side has to point up, that means our left side has to point down because they have to be opposite. And this is a generic graph for a leading coefficient that's positive, and then a degree is odd. The next one, it says the leading coefficient's negative, which means our right side needs to go down, and the degree is odd. So it's still going to have shift an odd number of times. 3 is an odd number, so that's what we're going to use. But the right side needs to point down. So it would look like this. Notice that they're just opposites of each other. The next one is if the degree is even and the leading coefficient's positive. Leading coefficient positive means it's going to point up, and if it's even, they have to go the same way, so they'll both point up. If the leading coefficient's negative and our degree is even, then they're both going to point down, because they both have to go the same direction if it's even. You should know those four graphs, because you're going to I'm going to give you some information, you're going to have to draw graphs later on. Know what that means, that if the leading coefficient is positive or negative, the right side's going up or down, and if it's odd or even, then the ends point opposite directions. Now all of this ties into end behavior, and for end behavior, what it is it's which way the ends of a graph point. Okay? Basically, do they point up or do they point down? And now we're not going to write up and down. We're going to use positive infinity and negative infinity, because these lines are going to go on forever. And for up, we use positive infinity, and for down, we use negative infinity. Now, there's a specific way that we write this, and we say as x, and then the arrow means approaches positive infinity, comma, f of x approaches something, and we'll fill in that blank. This first part is the right side of the graph. Okay? If we look at our picture over here, it's this part of the graph. It's what's on the right-hand side of the y-axis. The second one is almost identical, except we have a negative infinity, which stands for the left side of the graph. Okay? That's this part here, and it would be the left side of the graph. And we will fill in that blank also. Now, it's easier than it looks. The hardest part's actually remembering what you have to write down, because in these blanks here, we're going to fill it in with this part. We're going to fill it in whether it points up or it points down. And we've got an example here. Okay? And we're going to start by writing out as x approaches positive infinity, f of x goes to, now f of x is the y, so plus infinity up here means the right-hand side, and if we look at the right-hand side of our graph, which is this part over here, it's pointing down. Alright, so as x approaches positive infinity, f of x is going down. Well, we can't write down, so we say negative infinity, and that's all we have to do. That's half of it. That's the right-hand side. We have to do the second part of it, the left-hand side. Everything's the same except it's going to negative infinity this time. F of x goes to, we're looking at the left-hand side, and this time it's going up. We can't write up, so we say positive infinity. Now, all you're really doing is telling me whether it's going up or down. And again, you can't say up or down. You have to say positive infinity or negative infinity, because the line goes on forever. Okay, what we're going to do now is we're going to combine all this stuff together in two examples. Alright, and for each one of these examples, you're going to give me three things. First thing you're going to do is give the end behavior. Second thing is to state whether the degree is even or odd, and then the third thing is to state how many real zeros the graph has. So let's start with end behavior. End behavior is always going to be the same thing. As x approaches positive infinity, f of x is going to, and we're going to fill in the rest of that. That's the right-hand side, and then we go with the left-hand side. As x goes to negative infinity, f of x goes to, we're going to fill in the left. So let's look at our graph. First one is the right-hand side. It's pointing down. Okay, if it's going down, we fill it in with negative infinity. Now we look at the left-hand side. Left-hand side is going down. If it's going down, we fill it in with negative infinity. And that's all we have to do. Second part is to state whether the degree is even or odd. Now this plays in to when we talked about whether they're pointing the same direction or opposite directions. These are both pointing down. They're pointing the same way. And if they're going the same direction, that means it's even. Now you could count it out. You could count how many times it changes direction. And then this one, it changes 4. Goes up, down, up again, and then down again. And 4 is an even number. Okay, so if I specifically ask you for the degree, then the degree is 4. That means the greatest exponent would be 4. But it's even, and that's all I want, is whether it's even or odd. Number 3 is how many real zeros there are, which is how many times it crosses the x-axis. And if we look here, well, it crosses here and it crosses here. So there are 2 real zeros to this problem. And then that's all we need to give. Okay, we've stated the end behavior, stated whether it's either is odd or even, and then how many real zeros it has. This last one, I'm going to make this a pause and practice. I want you to try it on your own. 3 parts to it. So pause the pencast, see if you can figure out each part, and then come back and check your answer. Alright, let's real quickly go through these. End behavior, again, is always the same. Plus infinity, f of x goes to, and then as x goes to negative infinity, which again is the left side, f of x goes to. Alright, let's figure this out. Right-hand side is going up, so we put positive infinity. Left-hand side is going down, so we put negative infinity. That answers question 2 for us. We have one of each. They're going opposite directions, so it's odd. And if we actually want the degree, we count how many times it changes direction. It goes up, down, up, which would be 5. So the degree is actually 5. Third thing is how many times it crosses the x-axis. Crosses here, here, and here. So the real zeros are 3, and then we've answered the question. Now, one thing I want to point out is that end behavior, depending on what you're looking at, may be written one of 2 ways. The way we've written it is the first way, but sometimes they have it switched around on you. So like for this one, they would say, write it like this. F of x goes to negative infinity as x goes to negative infinity, and all they've done is they've switched it around. This part here comes second, but it's first the way we wrote it, so it's just flipped. So pay attention to that. I'm going to write watch this, okay, because that might happen depending on what you're looking at. And those are your notes for section 7.1 on end behavior, real zeros, and the degree, and how they interpret and how they work with the graphs of polynomial functions.